Now we begin the presentation on muscle physiology, and this is the first discussion on the contraction properties and the motor units. So this is the second in a series, and this picks up essentially where we left off with the previous presentation of thinking about a single muscle fiber, myofiber, or single skeletal muscle cell, versus an entire skeletal muscle. So here these set of images that we start with, graphical images, talking about the summation of contractions, is really with consideration of a single myofiber. However, we could consider the same thing for a full skeletal muscle if we were stimulating the full nerve that innervates that muscle. And again, the interactive physiology CD shows this quite nicely for a whole skeletal muscle, so I refer you there for that. The other point to be made, of course, is that we build on these concepts throughout the semester. For skeletal muscle, we move on to the next section of the first integrative physiology about the control of body movement, and we'll see a bit more there. For the smooth muscle, we'll see more of that with digestive and cardiovascular system. So there's many ways that we build on these initial concepts. So we orient ourselves always with a graphical display of what is on the x-axis, time in milliseconds, from 0 to 500 milliseconds, and tension, and they're not giving any units. They're relative units. It's fine. We don't need to see that. We definitely know that it is in a positive direction upward. So each time there is a stimulus, there is a contraction producing a tension of the same pattern over time and the same amplitude. And so the rate of climb and tension and the rate of decay and tension and peak tension, the amplitude of the tension. And of course the colored area is the area under the curve, so the area under the curve, if you recall a little bit of your calculus, would be equal for each of these. So a few different quantitative ways of considering what we are viewing here, these profiles of change in Y over time. So these are rate graphs. And we see again with a single stimulus the same exact pattern, and the area under that curve would match before, because the stimulus strength or intensity and frequency is not changed. If, however, we change just the single variable of the interval between stimuli, so the interstimulus interval, such that we reduce it to where there is a collision of the events, and in the previous presentation we showed the action potential with the latent period and then the tension building after the action potential had occurred. And so we said that it'd be possible to fire another action potential when the refractory period had ended for the action potential in the membrane, and there'd be enough time where the latency for that second event would add its initial tension onto what was already present, because it's the calcium concentration. So you'd be able to look at the area under this curve that is obviously different in profile and total amount of area than the response to a single stimulus, and it would correlate very highly. Both of these would correlate very highly with the concentration of calcium that was produced in the cell. So this idea of the two key limiting factors or essential factors for a contractile event, the calcium and the ATP, persists. And the presumption is that the ATP is going to be available. We know fatigue can occur, but at any starting point, with a fresh muscle, it should be there. So the changes that we observe are really related to the dynamics of the calcium. And I'm always talking about the diffusion around and bouncing here and there, and all of those types of statements. And the authors, of course, remind you of this more concisely and succinctly by saying, by the law of mass action. So, for example, to jump ahead in the text where it talks about the calcium concentration in smooth muscle, by the law of mass action, a decrease in free cytosolic calcium causes calcium to unbind from its binding site. That's another protein in smooth muscle. Here in skeletal muscle, the calcium would be unbinding from the troponin, as you recall, the calcium binding subunit. So if you can get enough calcium into the sarcoplasm before you get the complete loss of the prior contractile event producing tension, then you simply have an additive effect, and you can get a higher contraction from before. And it really is additive. So if you take this curve, if you picture it being here, then what is added on what we see as a higher event here is just the additive effect. So as far as I'm aware, it's additive. I don't know that it is anything beyond that, like a potentiation. The range of calcium that can be, concentration that can be produced within a skeletal muscle cell or a complete skeletal muscle is really quite vast. And it is limited, but it is quite vast, and so each muscle will have its own maximum tension profile based upon calcium calcium availability in its entirety, as far as maximum, right, pushing it to the limit, and the ATP and things like that, as well as the amount of the protein that is available. So a bodybuilder with a bunch of muscle mass has a lot more actin and myosin to produce a maximum tension in a whole muscle than a 90-year-old individual that has very little muscle mass entirely. So there's many factors, but we're trying to keep reminded of the total calcium that could be available to bathe the thick and thin filaments and be sustained over a period of time. So if you can keep putting it in there by having the stimulus interval close enough so that you have the summation of the contractions, you can reach a point to where you still have some up and down, so the calcium hasn't exceeded all the possible binding sites. It is decreasing just enough. The removal process can still take away just enough to have you drop back down in between stimuli, so you get this jagged tooth appearance of the tension wave, but it will not rise above a certain level with any additional peak. And this is, of course, the summation leading to the unfused tetanus, and it is dependent upon the interstimulus interval. If we ramp up that interstimulus interval even more, as you see here, we can observe a couple of things because we have sustained it over a significant period of time. I presume, still have the same, well, this is an uneven, so I'm not sure exactly how long this is going on, but it's going on long enough, certainly, for us to reach maximum, and then after some time period, again, depending upon the muscle cell type itself, or the muscle itself with the composition of the different muscle fibers made up in it and how you're stimulating the nerve. Anyway, based upon all those parameters, if they're all controlled, then it's just based upon the calcium that's available. You can get the calcium to be added at a rate faster than it can be removed, such that you get a smooth curve on the uprise, and it stays smooth at the maximal tension, and you cannot push it beyond that. And then, remember, it's that the law of mass action. If the calcium exceeds in mass, the total amount that can possibly be bound by all of the available troponin, then you get a very stable response that doesn't go any higher, but it also doesn't decrease. And then ultimately, even though calcium is available, other required factors, in particular the high energy phosphate bond, the ATP, is not available, or becomes less and less available, and the fatigue will cause the muscle to lose tension despite the continuing stimuli. So remember, we said that regardless of all the mechanisms that are associated with the producing the calcium concentration and the ATP concentration, we still come down to these two key factors. You can have all the calcium available that you want, and if you don't have the ATP available, then you're going to lose tension. So this is a summation leading to a complete tetanus. And again, the one variable that we changed is the interpulse interval. Now we can think of an entire skeletal muscle in the context of motor units, and this is where you are referred to the interactive physiology, the contraction of motor units. They have a very nice portion in there. We won't take any time in this recorded lecture to discuss that information, but we will build on it, and it certainly is available in other textbook resources should you decide to do that. And our textbook talks about it in a little more detail, and hopefully we'll have a chance to build on it as we proceed. So we are reminded of a cross-section of the spinal cord, a collection of neurons in the ventral gray horn that innervate skeletal muscle. These would be motor neurons, and we'll just come right out and call them the alpha motor neurons right now. And when we talk about the integration with their sensory reflexes, spinal cord reflexes, we'll add another population that innervates the skeletal muscle. So they're colored differently just to distinguish them throughout the length of their axon, and we can see their axons innervating different skeletal muscle fibers. And remember, they may not form just a single axon terminal neuromuscular junction with that. It may extend along its surface to a greater degree. But what is most important is that one single axon is producing or generating neuromuscular junctions with how many myofibers on their own. And there can be a 1-to-1 ratio or a 1 to several hundred skeletal muscle cells, myofibers as a ratio. So the size of the motor unit is different. The larger motor units are for gross movements, and the textbook talks about the different types of skeletal muscle fibers that are innervated by each. You have the slow fatigue type of skeletal muscle in the largest motor units, such as for body posture. So you can sit up all day long without a tremendous fatigue, equivalent to what you might be able to do if you were lifting a weight with your index finger that might tire early, or the bicep muscle where you're lifting a 100-pound dumbbell or something, if you could lift it even once. So there's a difference related to that. And it becomes very important, and we, through other activities, will build on that knowledge. Now, the mechanics of body movement, we think of the isotonic contractions, and we create force, and we move loads. So the concentric action is a shortening action. The eccentric action is a lengthening action. This is what we would be doing if we had the strength in our biceps to move the 100-pound dumbbell. If we couldn't, then we'd just probably do an isometric contraction where we'd create all the force we could, but we wouldn't move a load. It's supposed to be up there, but anyway. And in this case, we then are thinking of series elastic elements, where the sarcomeres shorten while the elastic elements stretch, resulting in little change in overall length. So in the initial presentation on the anatomy of skeletal muscle cells, we talked about parallel elastic connective tissue elements and the way that they contribute to the displacement of the stretch along the length of the muscle. The series elements are a more direct contribution. So this would be the skeletal muscle fibers end to end. If one skeletal muscle fiber was as long as the muscle belly itself, that's fine. At each of its ends, it's going to have a continuity with the collagenous connective tissue that goes into the tendon for origin on one end and insertion on the other end. And so when that skeletal muscle cell contracts, it won't be able to decrease the overall length of the muscle belly until it stretches and tightens the connective tissue at each of its ends, and then that stretch and tension is transferred through all the connective tissue within the tendons of origin insertion. Then you can begin to shorten the overall length of the muscle. So if you only place tension on the internal elastic elements in series and even those in parallel, then you create tension, but you don't get any movement. So that's the importance of thinking about that connective tissue component. So let's try to visualize that with an isotonic contraction here. So the tone will be the same, isotone, meaning that with that tone continued, as long as there's enough strength in the muscle, it can generate enough force to match and then exceed the load, it will then begin to shorten. So all of these variables must be taken into account. And so if it has the capability and the stimulus strength is such that it can match and exceed the load, then you can get a muscle contraction that will displace the load and shorten the length of the muscle over its entire distance. So we get a change in distance for the load. And then, of course, with muscle relaxation, you get the lengthening and the return. So there's so many different variables. Are you talking about the entire skeletal muscle? You could do this same study with a single muscle fiber, but you probably wouldn't have the series elastic elements, and the load would be applied to it differently. You wouldn't put a 20 kilogram load on a single skeletal myocyte. So try to keep all these in mind, because the general physiology textbooks, as we're using here, sometimes don't specify that, and they're leaving it to you to reason that, and that's why I try to bring it to your attention each time. So here we are now thinking of an entire muscle, and so we stimulate the muscle by whatever means. Typically it's a stimulation of the nerve, as you'll see in the interactive physiology CD animations, or any other type of animation you'd find. That's typically the way that they do it, or if you do it in the muscle physiology lab, if you take a lab course. And of course the tension will develop over time, and here the tension is shown in kilograms. We're not showing the force in newtons, we're just using kilograms, assuming that gravity will be constant. And then the force required to move the load can be generated, and then we see when the muscle relaxes, of course, the tension is reversed and proceeds back to zero. With the isometric contraction, so isometric, the length is going to stay the same. So we're going to stretch everything we can throughout the length of the muscle, the series and the parallel elastic components, by contraction of and generation of tension in as many of the muscle fiber cells that we recruit through the stimulus. and it will not be enough ever within these parameters to lift the load. So it could be the case where the muscle cannot generate even at maximal tension, recruiting all the muscle fibers that you could possibly recruit artificially by stimulation in an in vitro setting like this. Might never be able to match and exceed this, or the stimulus intensity that you provide in the recruitments of the motor units is not sufficient under the parameters that you're using. And you can see this with the animations. They've got a guy sitting at a bench doing the leg lifts, and you can select the muscle weight and then how many motor units you recruit, and he grunts and he grunts, and if you get too high of a weight without enough motor units, he just grunts and grunts and nothing moves. But anyway, it's kind of fun to watch it, so I hope you get a chance to do that. So the muscle may be capable of doing it, and you just don't have the stimulation parameters naturally or artificially in vitro to recruit enough muscle fibers. Either way, as you know, you generate a force that is less than, and I know it says tension here, but if gravity is the same, then we can kind of use the same term as force. Then the tension or the force that is produced does not match that which would be required to move the load. Well, let's take a moment then to let's see if they go through that. No, it's all shown on one slide. To think about the serial elastic components. We don't have a specific slide to look at the physics, the biophysics basically, of the parallel components, but it contributes as well. The series is one of the more directly important, because if you put a stretch on the muscle with some type of preload, it will stretch the elastic components first before it'll start pulling the sarcomeres to lengthen each individual sarcomere unit. As you recall, we looked at that graph at the end of the previous presentation, and I asked you to keep that in mind as we began to talk about whole muscle. So that was based upon a single sarcomere length. Now we're thinking about all the millions of sarcomeres that would be found throughout an entire biceps muscle. How can we imagine all of those? Well, we try to do it in a very simplistic form here of just looking at the sarcomeres that would be in series with a single elastic element at the end of the a single myofiber. So again, we're going to this reductionist approach to think of a single myofiber with the elastic attachments at each end of it, and trying to imagine in our mind all this coming together for an entire muscle. So obviously the dynamics are going to be a bit different for a whole muscle belly than they would be for a single muscle cell. So there's some type of cumulative contribution overall to generate a distinctive property for a muscle, and it depends upon the muscle fiber types, the motor unit recruitment, and a wide variety of things, as you might know. And the ratio of muscle fibers to connective tissue, including fatty tissue. So older individuals that have experienced what's called sarcopenia, the generalized loss of skeletal muscle fibers that occur in geriatric patients or other patients with certain degenerative muscle diseases, then obviously it's a very different behavior from the same muscle. The biceps muscle from one of those persons is going to behave differently than a bodybuilder, right, or a trained athlete in their 20s. Just the same, we have all the same parameters that we're considering here, and we see the muscle at rest, and with isometric contraction, the muscle has not shortened. The sarcomeres shorten, generating force, but elastic elements stretch allowing the muscle length to remain the same but to generate tension. And then with the isotonic contractions, the sarcomeres pass beyond this stage of 2, where the sarcomeres have shortened to some degree, and then they will shorten even more, such that they have exceeded the force necessary to generate the tension to straighten the series elastic elements, and then generate an overall reduction in the length of the muscle. So in other words, in a length of a muscle, the collective muscle fibers that are recruited, the distance of shortening for an isotonic contraction is the amount of shortening that remains after the shortening of the collective sarcomeres that's required to place the maximum tension on the series elastic elements. Right, so a certain amount of tension is required to stretch those to their maximum point, and then whatever remains as a shortening capacity within the collective sarcomeres is the distance that can be shortened maximally. And all those parameters can change. So you can have a preload, but you can also pre-shorten some so that you get a powerful movement over a short distance. So there's anybody that's into weightlifting, if you've ever watched the Olympics, you see the people that stretch their muscle and pull and stretch and pull, and they're putting weight on it, and then of course using their central nervous system to recruit motor units before they finally move it. So they're doing a little bit of these things here to generate the initial tension with an isometric contraction, and leaving themselves plenty of distance already available to move the weight and generate the force over the distance that they need. So the arm is a lever and a fulcrum system. So let's briefly introduce this concept. It's obviously much more complex and sophisticated than what we're considering here, but that's fine. We can manage. So we're thinking of the biceps brachii muscle originating proximally through the tendons of insertion, the short head here off the coracoid process, and the long head here off the supraglenoid tubercle, and they join together to form a common belly for insertion in this common tendon of insertion onto the radial tuberosity, crossing anterior to the elbow joint, so they are flexors. Their insertion is really pretty close to the elbow joint, and of course the load, if we're thinking of lifting a dumbbell, is quite far from that. And the fulcrum is the horizontal axis through the humeroulnar joint here. So we're talking about generating torque or a rotational force at this fulcrum. So that fulcrum, that exact midpoint here of a horizontal line coming through there, is where we would begin our measurement to measure the distance to the insertion of the tendon of the biceps brachii muscle, and then the contraction, the tension produced in the biceps brachii can generate a force across that distance, and that becomes the torque at the elbow joint. The second force at rest is roughly about 2 kilogram weight of a forearm. That would be the second force acting in the opposite direction, and we place that at the midpoint, the center of gravity of the forearm, which is about 15 centimeters away from the fulcrum. So in the textbook, it takes you through the formulations to calculate the rotational force. So in this example here, the biceps contraction creates the upward force, F1, and then it inserts the 5 centimeters away from the fulcrum. The rotational force up is approximately the biceps, or proportional to the product of F1 and this distance to the insertion. So F1 D1, if you want to think of it that way. And the weight of the forearm exerts this downward 2 kilogram force, and it's got the 15 centimeters. So the rotational force of that is the 2 times the 15. So to hold the arm stationary at 90 degrees, the rotational force created at the elbow joint by contracting the bicep must exactly oppose the downward by the forearm's weight, to give you an isometric contraction that would match that. So that is the biceps force times the 5 centimeters equals the 2 kilograms times the 15 centimeters. And then through algebraic manipulation of that, you divide both sides by this number here. And so F1 equals the product of these two, 30, divided by this, 5, so it gives you 6. So this force generated by the biceps has to equal 6 kilograms to hold the 2 kilogram arm at 90 degrees. Well, now we are asked how much additional force must the biceps exert to keep from dropping this weight, and this is a 7 kilogram load, so it's added at the hand, and this individual at 25 centimeters from the fulcrum. So we know that it's 7 times 25 will generate force 2, correct? And so I'll leave you to go through the mathematics of this, so it's asking how much additional force. So what this means is that if you just multiply the 7 times the 25, then that is the downward force, and you use the same formula, D1 F1 and D2 F2, to solve for F1, then that is the force required just for this, and you have to add it to the 6 that we got before, so that you have accommodated for the weight of the forearm. So in other words, the total load when you place 7 here is the 7 kilograms plus the weight of the forearm that you begin with, the 2 kilograms, right? So it's to calculate in this problem here the total force that this muscle has to generate to sustain this at a 90-degree angle when an additional 7 kilograms is added on top of the 2 kilograms that it weighs. Then you have the 2 times the 15, the 30, plus the 7 times the 25, correct? So think of it that way. What's the total force required, F1, at the biceps muscle to hold this weight, to hold the forearm stationary at 90 degrees with a 7 kilogram load added? That's a different question than what's the additional, how much additional force must the biceps exert to keep from dropping the weight? So run through that, get pencil and paper and calculator if you need it, and think about it. So the arm amplifies the speed of the movement of the load, as we see in this presentation. We're not going to go through any of the mathematics of it, but by having a very proximal placement, you can see that the distance that needs to be traveled proximally to produce 5 times that distance distally is quite short. It's 5 times shorter. I don't think I worded that quite right, did I? But you can see that the length of the lever attached at the fulcrum determines the amplification of the distance moved by the lever itself, the force acting at the lever. So the closer these muscles are attached, then the greater distance you get and even speed, but a slight reduction in power. The farther away these are attached, then the greater power that there is. And you'll see in the textbook that I teach comparative vertebrate anatomy course, and we go into all of these mechanics, biomechanics for animals that dig underground, and most of their muscles will attach farther out to generate the power. And then the fast animals have these close attachments to move with each contraction, to move all their legs a longer distance and faster. So it's a very important aspect of comparative anatomy. And if you are into athletics and you've observed different people's bodies, like football is a prime example, because you have the fast runners for the receivers and the running backs and the tackles, and the ones that have the power have certain body shapes, and you can almost see there's a greater thickness in certain areas. And then some of the fast runners will have the long, slender appearing musculoskeletal systems, even if they're really bulked up. So there is a range of differences among human beings, and it does impact their maximal capabilities. Then I think this is the one of the final slides. We just have a couple left. So we're obviously talking about the velocity. So besides those biomechanical factors that contribute to the speed with which you can change the distance or the position of the limbs or across the joints, there's also the intrinsic characteristics of a muscle and its response to a load. And so this graph is showing us the relationship of the preload on the muscle. So as we go from 0 to the right, we increase the load on the muscle, and the velocity of the shortening. So this is the load-velocity relationship. There are many different relationships for skeletal muscle, and we only touch on a very few in this course. So here we see that the load on the muscle increases to the point that you get 0 velocity. So this is like having the 100-pound load or 100 kilogram. Just do 100 pounds and not convert it. You can convert it to kilograms if you want to. Where most people can't lift a 100-pound dumbbell with their biceps just to flex their elbow. So you are going to have a 0 velocity of shortening. The development of tension may be different. So a load-tension relationship might be different than the load velocity of shortening. So this is only talking about isotonic to the point where isotonic is disappearing as you increase the load to a point where you have only isometric contraction. Anyway, with a light load, you can move a pencil a lot faster. Pencil in your hand, you can flex that a lot faster than you can 5 pounds, than you can 10 pounds, than you can 50 pounds, than you can 100 pounds, right? So that's what this is pointing out to us here. So there are some biophysical limitations, and it generates a non-linear decrement as you increase the load. So that's important, is to recognize that it is not linear. That means that it's a complex system of events that is occurring, and this can be observed with a single muscle fiber as well as a full muscle belly itself. Then we can consider some muscle disorders. So muscle cramp is a sustained painful contraction. These can be brought about by a few characteristic changes in muscle, like the accumulation of lactic acid, as you know, and overuse, disuse, and atrophy. We're all familiar with that. The acquired disorders and inherited disorders. So obviously I'm going to just present this as a list for the sake of time, and you can do a little bit of additional reading in the text for this. I hope that I can get some case studies that will cover some of these for you to learn a bit more. Under the inherited disorders, Duchenne's muscle dystrophy is an important one to consider because the gene is known. So again, if they're inherited, it's because of a gene, and there's a range of nucleic acid sequences in the gene, and some of those are considered as mutations that produce abnormal function of the proteins. It might be a complete loss of function or a gain of some other function. When it is known, then we of course have a greater handle on how we might be able to treat the disease and hopefully cure. McArdle's disease as a myophosphorylase deficiency glycogenosis. The glycogen is not converted to glucose 6-phosphate, so you produce glycogen, but you don't break it down. And then finally, as we are transitioning away from skeletal muscle to smooth and then ultimately cardiac, we want to start thinking about the duration of the muscle contraction in these three types of muscles. So the skeletal muscle has the shortest duration, cardiac has the next longest, but they are within 1 second. The skeletal muscle is out to a few hundred milliseconds, as you recall, and the smooth muscle can extend out for approximately 5 seconds, and so you are aware of if you've ever breathed something in that closes up your throat a little bit, makes you kind of cough a little bit, that extends for a longer period of time than just a simple twitch in your skeletal muscle to bend your elbow. So this will be the final slide. The next set will talk about smooth muscle, so we'll come to understand why it has such a long duration of contraction related to the molecular events that produce it. Then we'll see some characteristic aspects of the cardiac contraction paralleled by the action potential when we get to that. So remember that the action potential is already completed in the early part of the generation of tension in a skeletal muscle. And then we'll see that the action potential covers the entire time period of contraction cycle for contraction relaxation cycle, I should say, for cardiac muscle tissue. We don't want summation in cardiac muscle tissue, right? And then smooth muscle is quite a different style of regulating the release and removal of the calcium. And we'll see how that's important to generate this type of a duration for the organ systems that contain smooth muscle. We'll introduce it and then, of course, study it in more detail as we proceed to the different organ systems through this semester. I appreciate your time and attention, and we'll see you in the next presentation.